Hello everyone, very good evening and welcome to another session on banking analytics with respect to supervised learning in association with 360DigiTMG. So today we are going to discuss about supervised learning model. In supervised learning model, the other 2 days we have discussed about two classification model building, two classification machine learning algorithms. Today we are going to discuss about regression. Today we are going to discuss about regression. So it all depends upon the accuracy. So the predictions are happening in numeric form. If the predictions are happening in numeric form, you will go and apply regression technique. So what is this linear regression? What is regression? When y is known to you and y happens to be numeric in form, you have to apply linear regression. So there is a concept which is called as dependent variable and independent variable. So the point here is you are trying to find out the relationship between these two. So we have understood as a part of our previous discussions that we are trying to find out the relationship between these two, where x can be anything and y is always dependent on x. X can be anything. So x1, x2, x3, it is your choice. They can be anything. These are nothing but the features. You call them as column names, or you can also call them as variables or dimensions. So for any given value of x, you are trying to find out y. For any given x, you are trying to find out y, and this is your y hat, which is called as the predicted value, which you call it as predicted value. So the point here is, suppose you want to find out the profit of your bank, right? Whether your bank is at profits or not. So you do a lot of marketing regarding that. So amount of marketing, amount you spend on the profits you gain. So the point when you collect any input for your analysis, you're trying to find out the relationship between these two. If the marketing amount you're spending, is it really giving you profits, right? Or it is a straight line is what you're trying to check. It is nothing but we are trying to find out the cause and effect relationship between two variables. It is input and output variable. So in two-dimension space, when we want to find out the relationship between both of them, such a plot is called as a scatter plot. It's very, very important that you cannot take any inputs, whatever you want. You cannot take any inputs of your choice for predictions. It's very, very important that the input what you take and whatever analysis you are doing and whatever you want to predict should have some good relationship, ending up with right predictions and very good accuracy. So in terms of classification models, we got a crosstab. We used confusion matrix. Using confusion matrix, you have calculated accuracy of the model. Here, because their prediction happens in categorical form. But here when we are talking about this, the predictions are happening in numeric form. You have to calculate the error. Error is very, very important. Okay, error is very, very important here. So while discussing this concept, right, the performance of the banking industry, it is very, very important in determining the stability of your bank in any country you take. It is any country, any state of any other country. If you take, the performance is very, very important because of the technological advancement which has created heavy competition in the market. This affects not only banking industry, all the organizations here, regardless of any business you take into consideration. So of course, now banks are also no exception here. They have to compete not only among the banks across in that particular one local bank or two other local banks, but also they have the competition with foreign banks. So situation requires a need for the decision makers. You should be able to take accurate decision. And so you have to do some mathematical analysis whether our performance, are we at profits when compared to any other bank. So determinant of the bank performance and variables used are very, very important for prediction. So when it is a description of the input variables, you should have very, very good impact in prediction of your profits. So whatever plot we have done, it is giving us very good indication that whatever inputs we have taken, are they really important for our prediction or not. This is one plot which is going to help us. So the point here is, if at all I have to predict the profit margin of one particular, if at all I have spent, this is a scatter plot I have. Okay, this is a scatter plot I have. This scatter plot is telling me that I have a very, very good relationship. Okay, I have taken one easy variable, which is marketing strategy, what amount they have spent on the profit of the organization of the bank. So what I do here is I have to predict for a certain amount. Now they have spent around 50,000, 1 lakh, 2 lakh, 3 lakh, or 4 lakh, like this. So you got the scatter plot. Profits are also increasing in that way. Huge number of profits. So what happens suddenly, I want to predict if at all I spend 2.2 lakhs or 2.5 lakhs. If at all I have to spend 2.5 lakh here, let's assume that now the relationship here is a linear relationship and I don't have any value which is mapping onto 2 lakhs or 3 lakhs. If it is 2 lakhs or 3 lakhs, okay, whatever value you take, that value you are taking, it should map to either 2 lakhs or 3 lakhs. But we don't have the exact value here. So what will I do? I'll just take this point in between these two. I'll join this. Okay, I'll try to join this and I'll map to this. Expecting profits for an ungiven data, estimate. So I will try, I guess that I have a line like this and I try to estimate it for an unknown value, and this happens to be, I say that this matched here and this is the value what you are predicting, you are telling the future. This is your predicted profit value. You're checking the intersection. If I try to see what is my y value, I got my y value. This is nothing but y hat, which is my profit, which is my profit hat, which is a predicted value. So this concept is called as regression. This concept is called as regression. How do you find out? If the data is scattered, you are interested to get the best fit line. The point here is, why should I always get a straight line? I may get a line like this, I may get a line like this, I may get a line like this, any line I may get. The line, whatever you are choosing, should capture maximum information so that that is the best fit line. Your algorithm should give. Your algorithm should give you the value, the line which will capture maximum information. Maximum data points should fall on the line. But there is a chance that few data points are ignored. Okay, there's a chance that it may not always capture all the line what you are drawing may not capture all the lines in a single go. You may get a line like this. Right? So how do you measure that particular value? So you are interested in this best fit line. So you're talking about the regression line. Generally, the equation of a straight line is y is equal to mx plus c. So when it is mx plus c, now y is your output, m happens to be your slope, and c happens to be your intercept. And x is your input. So if at all you are trying to check the line here, if the line is something like this is your constant value and this is the slope. This is your m. This is your y, this is your x. Relating all this, you are writing this regression equation. Y is equal to mx plus c. Using this concept, we are getting the equation which is nothing but beta naught plus beta 1 x1. So where beta 1 is your slope and beta naught is intercept C. Beta 1 is slope and beta naught is intercept. So the data point, whatever you are estimating, okay, the data point, whatever you are estimating, that data point will fall on the line. Okay, that data point will fall on the line. 1 minute, my bad. So that data point which is falling on the line, you will take that as your best fit line and the best predicted value. So do you think the data point would always fall on this straight line? Not really, right? The data point may not always fall on the line. This is what you have. You have the scatter. You have the scatter like this. Okay. So tomorrow when you don't know any value, you have to predict for this amount you spend on marketing, you are just mapping onto a line. This is my C. Okay. This is your predicted value. Okay. This predicted value, you are telling it as this as your y hat value because it is hitting this straight line here. But for our convenience, we are saying this, but if at all the actual value happens to be this, if the actual value happens to be that, this gap, what you are seeing is the error. This is the error term. For any input you give, always it is, we see, we are not, fortune tellers that whatever we predict, right? We are going to, it will be 100% correct. It is not 100% correct. There will be some mismatches because we are building a machine. We are asking the machine to learn. So machine is giving me this value, but this is my actual y. But this is what your model is telling. This gap, what you're calling it as error term, which you add to your regression equation line. Adding the error term here. Right? So, like that, if you have different values to predict, right? Are you not getting different errors like this? For all the data points, for all the amount you are entering, all these are errors. This difference is error. Right? You have to find the line which will give you the least error. You have to check with the line which will give you the least error. Okay, that is the concept of linear regression. Algorithm is going to give you, okay, algorithm is going to give you the values which are nothing but your beta naught and beta 1. You are calculating your error term, and the best model here is which is giving you the best beta naught beta 1, where you get this value nearly equal to your y. This value which is nearly equal to your y, because everything happens here in numeric, everything happens in the continuous and it is numeric in nature. we are calculating this something called as root mean square error. You calculate your actual value is y, you calculate the predicted value, you subtract it. Y minus y hat is your error. But error can be positive, error can be negative. Both can happen. Error could be positive, error could be negative. Both can happen. But which is very, very important here is this error. This error, whatever we are getting, that will nullify it if you add all the errors. Now, plus side and minus side, you are getting the errors. So what you have to do? You have to square the errors. Errors, square the errors. Take the first error, error square, average of these errors. But error cannot have units like dollar square, miles square, centimeter square, because units are something which are getting influenced. So what will you do is you calculate root mean square error. You do square root of the error, whatever you get. So this is going to give us root mean square error, which is a final error for your model 1. But there are few things which we have to focus here, which is nothing but this equation, whatever you are getting, the root mean square, whatever calculation you are doing, we have to check the relationship between two entities. Okay, the relationship between two entities should be good enough. Entities or variables, whatever you are checking, right? If at all you are working with continuous data, there is a concept called as normality. Check. First important thing is y is your output, x is your input, very good. But what is that? Y is equal to mx plus c. What is this x? Are x and y are having very, very good relation or not is what you are concentrating. But important thing is statisticians have designed something like if at all you're applying any linear model, whether on any data you want, right? That data should be normally distributed. The data should be normally distributed. Whether you take any asset, you take like we have written the output here. So to determine the bank profitability, I can take all these measures into consideration. Right? Dependent variable, this happens to be my y, and independent variable happens to be 1, 2, 3, 4, 5. Either I can take all of them. Okay, either I can take only one variable. I have to check. Now, if at all I have to take all these variables, this is the table, looks like this. Liquidity, credit risk, cost income ratio, size. And this is I have taken the data which will pick up different banks, and I want to know which bank is it more profits. Considering all the 7 variables which are the inputs for us. So how will be your equation will come here if you are working with this? Okay, if at all you're working with this here, with this data here, you have to work with, let me write the equation, how it looks. It is nothing but y is equal to, you have to predict the profitability here, net profits or the assets, which is equal to beta naught, which is a constant. Beta 1 is given by the algorithm. X1 is what I have taken, which is the GDP is what I have explained you. I have to take liquidity plus, if at all I have to take credit risk plus beta 3, cost income ratio, and I have to take in real assets, what is the size, which is beta 4 plus inflation, consumer price index, which is 5 plus beta 6, which is economic activity. right? So what is that which is very, very important as a part of regression is that these are important for this prediction or not. That is the first thing, right? These are important or not for those predictions. So the underlying assumptions are there here for the linear regression, that y should have very good relationship with x1 to x7. But these among themselves, they should not have any relationship. Okay, no relationship between inputs. Every input you collect, they should be independent of each other. They should not have any dependency among themselves. Okay, that is the first thing. And it being out of all this, how many are, if at all you have all these things as numeric, if they are numeric in nature, right, there is a concept called as normality check. Okay, you have to do the normality check. Sorry, my bad. Okay, this normality check is nothing but if you try to plot that particular data, that input, okay, it should be like a bell curve. It should be a bell curve. Okay, there's a formal way is that you do some plot called as QQ plot, which will help you to find out whether, what happened to this? Sorry. There's a plot called as a QQ plot, which talks about the normality check. If at all you're working with continuous data, this is a mandatory thing what you have to check. If you don't check this and you move forward, it means that your underlying data is not normal. Still you are going and going and building the model, your error will be more. So instead of facing all those problems, we have to take a call here only, check the normality of all the input variables and move forward. So when you will call it as a linear regression, if at all you have only one input, you are trying to find out the relationship between input and output. With one input, it is called as simple linear regression. Okay, here I'm talking about yearly data of the bank, maybe from 13 banks, 10 years data if we take, randomly selected from one particular country, right? Data for all the variables you have collected from different sources here. Predicted variables should be significant enough for this. So while discussing this part, okay, we are interested here for this. The point here is, let us understand here what is that we are going to do. The first point here is I am importing NumPy, Pandas, and MyPlot, and I've just given a data set, but this is a data. Because I'm only explaining here the concept of simple linear regression, I'm only interested in this one. One input, prediction and output. Okay, so according to GDP of that particular country, of that particular state, what is a profit? Is it really influencing the profit or not? I don't know. I have got the data, that particular bank has given me, that particular sector has given me the data, and I cannot blindly follow the raw format of the data. I can have marketing strategy, I can have consumer price index, as I told you, I can have any other input, liquidity. Any input I want, I can take. Right? So if at all I want to find out, the average assets, return on average assets, if that is a predicted variable, what all the other inputs I can take? I can take GDP, I can take consumer price index, I can take cost to income ratio, right? Loan loss provision to the loan with the loans ratio, loan to assets ratio as a measure of liquidity. Many things I can take, but if at all we are working with only one input, we are calling it as linear regression. Just taken one input to predict profit related to state column. State is one column I have here. Very, very small data set I have taken here for analyzing here. this concept of regression. The first and the foremost thing what you do is, this is my data. I have to check whether GDP is really important for my prediction of profit. It might be important, it might not be important. I am clueless, but I have to do that. So first and foremost thing is that if it is a numeric data, you have to check normality first thing, and your y and x should have linear relationship, and that relationship should also be strong enough, because you're predicting something for any given value of x. Predicting something for any given value of x. So when you're talking about a scatter plot primary purpose, if you do a scatter plot, it gives you some insights. Every plot we handle, it will give you some insights. Like histogram talks about the normality check, skewness of your data. Like that, primary purpose of the scatter plot is it talks about the linearity. Okay, it talks about, are they having in the relationship is in the positive direction like this. Okay, and how is the strength? What is strength actually here? Strength is nothing but how impactful is my profit, and how impactful is GDP on profit. So if you look at this plot, it's almost there in the same range. And if you see, observe the magnitude, I think it is something like this, leaving 2 or 3 data points. So very small data set, they are okay only. You know, the magnitude is not that much varying. But I cannot say that how important. I can say that, okay, it is good only to predict this. But how important is this for prediction of profitability? I don't know. So what I should do, whatever strength I'm talking, which is subjective in nature, means someone may say that both of them are having weak relationship, both of them are having moderate relationship. Some may say that both of them are having strong relationship, which is subjective. Subjective means everyone will have their own perceptions. Everyone, they have their own perceptions. One may say that Alia Bhatt is more beautiful. Some may say that Shraddha Kapoor is more beautiful. It's a perception. It is subjective in nature. So to quantify that, okay, to know that whether this plot is good enough or not, you should find something called as a correlation coefficient. Okay, you have to find out the relationship between two entities, and you want a number to quantify it. You should have a strong to explain that in the project charter, the high level document what you prepare when the project is given to you. You should be knowing that what is the relationship between the two entities you have taken. It is called as correlation coefficient. It's called as correlation coefficient. So this is, if that particular value, see what I have done, I have just taken this. I could know that if you see GDP to GDP, it is 1. Profit to profit, it is 1. So this is what my number is. So you can say that if that particular relationship between two entities, two variables, if it crosses 0.85, they are into strong relationship. Okay, they are into strong relationship. If that relationship here between both of them if at all there is a strong relationship, it is 0.85. If anything between, this is very, very weak, means you are not taking this input, it is a blunder. Your approach is wrong, you end up with wrong analysis, is what you are going to do. This is what you are going to do. Okay. So it's very, very important that whatever inputs you take, you do kind of feature engineering, you find out the relationship here. But this is something which you get, it is in between 0.85 to 0.4. You will put it here in the moderate. but you are helpless. You have to take this input only. They have only this input with you. They did not give you consumer price index. They did not give you liquidity. They did not give you any other input. The only thing which is available to you, you have to utilize that particular input. So that's how you start analyzing the data. So once we know that it is moderate, still you can move forward and go and build the model. But whatever input you have taken here, that input is numeric. So GDP is something, what you are writing, it is input, is numeric. So what you do is you have to do a plot which is called as QQ plot. Okay, if 50% of your data is falling on this line in a linear form, so when you call it as a linear from this corner to this corner, you draw a line and data points should fall on that line. Okay, then you say that this data is normal data. This is a mandatory check. This is a mandatory check. So when you are checking this, okay, when you are checking this point, it's that you are doing, which is nothing but, if you see maximum data points are falling on the line, only 1 or 2 are out of line, right? This plot is called as QQ plot. The plot we are doing here is, it's not available directly in matplotlib because it is it's the two things you want to do here. It is a line what you have to draw, and also you have to draw the data points here. Line should come, data points also should come. Where this is your values, this is your standardized value. So I've just taken for GDP and happy that it is normally distributed. I can move forward. There is no question of GDP being not normal. So assuming that everything is normal. Okay, suppose in case, if at all I get less accuracy because the correlation between both of them is 0.74 only. But if it is 0.85, I'll be happy. I'll be happy, but it's only 0.74. I'm not sure that my model is going to work. Absolutely fine. Good. Okay. So to build this linear regression model here, we have to pull in statsmodel.formula.api as SMF. So it's nothing but statsmodel.formula.api, which is going to give me OLS technique. Now, what is this OLS technique? Whenever you are trying to draw a line, the best fit line, okay, you have the data points. These data points are falling on the line like this. Okay, and you're calculating the error. Deviated. They got deviated here from the line. You are telling this is my predicted value. Okay, this is your original value. Dots are my original value. Right? Dots are my original value. These dots are my original value. But if they are touching this line, this is my predicted value. This is my predicted value. So many times predicted value will be nearly equal to actual value. But the line what you are drawing and the prediction what is happening, it should be least. So OLS stands for ordinary least square error. It's called as ordinary least square error. So this ordinary least square error means you want a error and the line, the best fit line, so that maximum data point should fall on the line, and this error what you are calculating, actual value minus predicted value, actual value, predicted value. That should, if you do some of the square errors, it should be least. If you do some of the squared errors. So that is OLS technique, which is available in statsmodel.formula.api. And the formula is y tilde x. What is my y? What is my x? This is my data. I'm fitting it. So fitting my model, taking only 2 inputs. Okay, once I check this summary here, this is the summary. So as I told you, your y hat, which is equal to beta naught plus beta 1 x1, you get your beta naught. This is your beta naught. Okay, this is your beta 1. So 6 into 10 to the power of 4. Okay, the interpretation plus 0.2465 into GDP. What it will do? It will take each value of your input. It will take now 471, 784 value. Okay, it will come here to substitute 6 into 10 to the power of 4 plus 0.2465, 461, 798 or something. You get the predicted value. This is my predicted value, what I got from the model, but my actual value here, if you see, this is the actual profit. 19,22261 is my Y. This is my predicted value. This minus this is my error. This is my actual value. What model gave me is, after substituting this value, it is my predicted value. But the point here is, whatever if beta naught, beta 1 values it is giving, you can accept them just like that. You cannot accept them. You have to check whether you can accept these two values. Upfront, you can accept it if you check your p value here. So we'll not get into the stats much, but you have to check your p value. If p value is less than 0.05, you can accept your beta naught and beta 1 values. Suppose if your p value is not greater than 0.05, if it is greater than that, you cannot move forward with these beta naught, beta 1 values, what algorithm gave you. So it is industry standard, and it is like, the thumb rules are there, right? So we are not into research here. We have to accept these thumb rules. Okay, so this is something what you have to check. Now I have these two values. Luckily, we are having these two values here. Okay, the other thing is, if at all you are going with this equation, whatever equation you got, you want to accept this total equation. Okay, we have to check these two p values. The other thing what you have to check is there's something called as R square. This is very, very low. It means that if at all I'm giving 100 values, it is only able to predict 56 values correctly. This is one more problem. So the model is not good. Model is OLS technique. I have 50 here, observations here, right? 0.559. So I have to improve this. So maybe I have to add now consumer price index, liquidity, other inputs what we have discussed. So, but I want to know what is the error. Right? These are the two things which you can mention the project of that GDP is not alone important for prediction of profit of an organization. So now ML1.predict, this is my model I'm predicting. I'm asking you to take GDP and give me the predictions. These are my prediction values. Means all that line, the data points are touching the line. So what will I do is, how is the line? This line is my regression line. This regression line I take, okay, this regression line I take, and this is the best fit line is what I have to come from. Right? This is the line what my algorithm gave. These are my original data points. Original data points. So now question to you all is, if I am having my y-axis being profit, this is my this one. Okay. If you observe here, the data points are in sync like this. Okay. There is something which you have to focus here is, you should not have the spread like this. If you observe here, for one particular input, see here this input is almost on the line. Here the error is equal to 0. But for this person, for this value, this is the error. See the error very less, very less. This is okay. But for few data points, the error is very huge. 1 or 2 data points, if the error is huge, no problem. You will accept the model. But you have to build a model for any given data, for any given value. You're upfront, you want a model to predict the value which is more relevant, like which is more near to the actual value. Right? If you observe now the error, same model. So error for one input is more, error for another input it is less. So this problem is a problem here. It is called as heteroscedasticity. It is called as heteroscedasticity problem. So it is important that your values should fall in sync like this. The magnitude will not vary. So the errors should be constant. The variance should be constant, I can say. Okay, the variance should be constant. If that is not happening, you cannot move forward. You cannot conclude. You cannot go for deployment of your model. You cannot go for the deployment of your model. Okay, so there is one thing you have to focus. Now, how do you calculate the error for this model, whatever you have built? You will check. This is my original value, y. This is my predicted value. Y minus y hat is the predicted value. Minus, sorry, actual value minus predicted value, which is equal to RES1. Okay, so now this is my error. I'm doing error square. I'm taking average of my error square. To get back that, I'm taking square root of this, which is called as root mean square error. So whatever things we have seen, we did not see no hetero problem, no heteroscedasticity problem. But the problem what we could see is the correlation is 0.74, right? And I got an error, which is 264.92. Okay. And also one thing is that input what you have taken is normally distributed. But the flaws here is this is one thing which you have to focus. Another thing is your R square value, which is nothing but 0.55. This is one thing what you have to focus. Error is something what you have to focus. It means that error is more only. Why? Because you have R square value 0.55, which is worst of the worst scenario. R square is called as coefficient of determination. It talks about how well your model is, how well the inputs are, how well your best fit line. So how well it talks about how good is your input, whatever you have taken. So if you are not getting good input for prediction of y, you will end up with wrong analysis with worst R square value. So one thing we can draw a conclusion here is that you have to come up with a different input. Maybe amount of marketing amount you spend to gain profits. You do a lot of marketing, you want to withstand. Nowadays, we see that, banks, you don't have your account also, they're offering you credit cards. You don't have account also, they are offering. Such a situation they have come up because it is a strategy what they want to play around to withstand themselves. So one thing is that you have to take a different input to check the profitability. One conclusion you can draw, or else you can apply some kind of transformations to your data, to the column, so that you can improve your R square value. Right? Or I can instead of writing R square value, to improve your correlation coefficient, to improve your R. So the main point here is whenever you are working with linear regression, it all runs with assumptions. It all runs with assumptions. There's nothing like this is perfect enough, but these assumptions should be perfectly done. These assumptions should be followed. Okay, then only the analysis would go in a perfect way. Otherwise, after you complete your crisp MLQ process, you understand the problem, you collect the data, then you do a lot of feature engineering, right? And then you are kind of building your model, then you're getting the error, you're deploying the product. Once you deploy the product, you cannot go back to step 2 here. And you cannot go to the step 2 concept here. So this is something which is you have to focus. So the point here is you have to check for your outliers. You have to check for your skewness or not. You have to check for normality check. Right? So all these will lead to a point where which is called as assumptions of linear regression. Right? Assumptions of linear regression. So the point, what are the assumptions? Okay. So what is it which is very, very important here? That the relationship should be linear. Errors should be constant. Okay. The correlation coefficient should be greater than that. And your inputs, whatever you take, they should not, don't have any relationship. Okay. They should not have any relationship. And what is the other point? This, if at all they have relationship, again you have to solve. Okay, errors should be constant. And what is it you are doing here is, and the sum of the squared errors should be least. And so the evaluation metric here is RMSE. It is nothing but RMSE. So this is your linear regression. So adding more inputs is what I can do. I can take this data. Okay, I can copy, I can collect the data from various sources. Here, I can check the credit risk, I can check the cost income ratio, I can collect all these factors, I can build a model, which will lead, where your all line assumptions should be fulfilled, and also it will give you appropriate predictions for the data, because one input is not solving our problem here. One input is not solving your problem. It is something what you have to do is you have to check this with different inputs. So results of this is something what you have to do, calculate here is error you have to calculate. So I just took GDP here, economic activity, what I have taken is GDP, but to my surprise, I have got R square to be very, very less. It is 0.55. So the R square value will stand between 0 to 1. Okay, with 0 to 100% I can take. Okay, it's the 0 to 100%. 100% is great. Now we got only 55. So with one input, and that could be one reason. Another input is that it is only 0.75 is what you got R, that is correlation coefficient. But good thing is that you have your p values significant, right? But if you take these inputs, you have to check whether they are independent to each other or they're having a relationship. So if at all they have relationship, again you have to solve that, because the problem of collinearity also will not give you proper analysis, right? It will not give you proper analysis. That is the concept here, right? This is the conclusion what we can take from our analysis. So given that, now what I can do is, because I don't have any problem of heteroscedasticity, okay, I found that the GDP what I've taken is normally distributed. Okay, I can stop here. But if at all I could get some other, they are not normal, still that relationship is not good enough. So what will I do? I'll just go and apply transformations to my data. Because data is not available readily with us. We have to collect it from various resources. So apply transformations here. What will happen? I can make it into log of GDP, reciprocal of GDP, GDP square, or GDP square root of GDP. All these transformations I do, if at all I have heteroscedasticity problem. Okay, if at all I have this heteroscedasticity problem. So the good thing is that these are the values what you are going to get from the algorithm. And this is the value what you are going to get, p value. P value is nothing what you're checking with your significance level. That is the standard what you have to check. So these two are going hand in hand. Adjusted, if at all you are adding one input. Now we have so many inputs here. Your consumer price index. You have added this input. If you are adding this input, what is going to happen is your R square will increase. But this is important, not important, R square will increase. Right? You added one more liquidity, one more column. The R square will increase. Whether liquidity is important or not important, also R square will increase. So now one more input. If you take here cost income ratio, if you take this cost income ratio also, adding one more input. So what is the equation here? It will become beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Then to improve your R square value, to improve your predictivity of this data, the R square keeps on increasing if you keep on adding your inputs. But added inputs, how relevant are they for prediction of Y, for profitability? It is important or not important, R square will not care at all. Keeps on increasing. You have added liquidity, you have added CPI, or you have added any other input, your R square value keeps on increasing. So to counter that, you check with adjusted R square. To counter that, you check with adjusted R square. So these two should go hand in hand. There should not be much difference. If there is much difference between them, it means that whatever added input you have, that is not relevant. If it's a raw data what you're taking, it is not relevant. You can delete that column upfront, you can delete that particular column. So this is, people still see, when you have something like deep learning algorithm, very sophisticated libraries are available to do lot of analysis, still people are going and using linear regression, regressive models. Is only that the interpretation of regression analysis is very, very good. Every input, you can detailedly understand what is his input, how is it input, is it important for prediction of Y or not. This explanation capabilities are only available through analysis, which is regression. No other, you will not get any other, what you call it as algorithm which is going to give you this explanation capabilities. Because tomorrow when I'm going to explain you the artificial neural network, which is the last algorithm what we are going to discuss, it is artificial neural network. It will not give you anything. You give the input, it will analyze, it will give you the output. There is no question of checking of this analysis, no checking of collinearity problem, no checking of normality, no checking of correlation coefficient, R square, nothing, P values. Just take the data, drag, drop it, pull in, pass the data to the architecture, give the output. It's a high level end of using and working with the data. But when it comes to regression, it is explaining things in beautiful manner. So to analyze and to know which are the relevant inputs, we are going for regression analysis. So still in demand, still in as the top one model building machine learning model is regression. The only reason interpretation is very, very at high end. Okay, so tomorrow we are going to start with artificial neural network, which is a deep learning algorithm. So thank you all for joining in.